Hello and welcome back to the lecture on applied econometry. So in this lecture we are going to talk about
autocorrelation, and in the previous lectures we introduced Darwin-Watson statistic as a test of autocorrelation. Now in this lecture we are going to talk about another test, that is Breusch-Godfrey test, which we use to sort of get rid of certain limitations that you have seen in case of Darwin-Watson statistic. So if you remember, we actually outlined some of the limitations that you can see in Darwin-Watson statistic, and one of the most important limitation for Darwin-Watson statistic is that it is only applicable for AR1 process. It is only applicable for AR1 process. What do you mean by AR1 process? What do you mean by AR1 process is that the error term of tth period, so we write the equation is like that, ut is equal to rho ut minus 1 et. So the error term of the tth period ut is only related to the error term of the previous period t minus 1. Alright, but it is not related to any other previous error term, so which is basically that would be indicated by higher order AR processes. So let's say AR2, AR2 process would be represented, if I write down the error term, so it will look like ut is equal to, let's say, rho 1 ut minus 1 plus rho 2 ut minus 2 plus the innovation term. Okay, and similarly if I keep on writing AR3 process in the same manner, I will write ut is equal to rho 1 ut minus 1 rho 2 ut minus 2 rho 3 ut minus 3 and the innovation term. Alright, so this is how we'll write, but these are the processes for which Darwin-Watson statistic cannot be used, okay, and that is a problem. So for this kind of situations, when we have higher order AR processes, we can actually use the BG test, Breusch-Godfrey test. Okay, so in these cases, Breusch-Godfrey test is applicable. The second limitation that we have seen in case of Darwin-Watson statistic is that we cannot introduce the lag dependent variable, no lag dependent variable as regressor, as regressor when we are regressing, when the dependent variable is the error term. Okay, so we have seen previously that we actually identify a regression equation, and from where we actually do the prediction of the value of rho 1 or rho in this case for Darwin-Watson statistic, so that we cannot, in that equation we cannot have the lag dependent variable, no lag dependent variable in the or as regressor in the when the dependent variable is the error term. I just explain it. Is the error term. Now there is a problem with this. The problem is, if I cannot introduce the lag dependent variable or any of the independent variables of the original equation into the equation of the error term, so what I will have is that I may actually end up violating the zero conditional mean of error term. So zero conditional mean of error term, we have seen this is written, the error term, this conditional mean of error term is written as this. So this condition may get violated. Okay, and I'll explain how this is happening and why, by the inclusion of lag dependent variable, this condition actually, the violation, the condition, basically the violation may be avoided. Okay, so this condition may be violated, and this is one of the conditions for Gauss-Markov assumption. So we need to sort of maintain we sort of uphold this condition when we are doing the regression of the error term. May be avoided, condition may be violated if violated in DW statistic. Okay, and that happens because we cannot introduce a lag dependent variable in the regression equation. Now let me explain what I'm trying to say here. Now let's say we have the original regression equation is something like this. Let's say my yt is equal to some beta 0 plus some beta 1 xt1 beta 2 xt2 and some t2 and some ut. Alright, now ut here is the error term, and the problem that we are trying to deal here is that we are assuming that ut has some autocorrelation structure, and we have seen, let's say in this case we're talking about a AR2 process. Let's say I'm assuming that ut has a AR2 autocorrelation structure. So ut would be written as ut is equal to rho 1 ut minus 1 plus rho 2 ut minus 2 plus some innovation term. Alright, now what would be the hypothesis test for this? So my H naught would be all the rows are 0, because my autocorrelation, in this model the autocorrelation is 0, so that if that is the case, so then all the rows are needed to be equal to 0. Okay, whereas the alternative hypothesis goes like this, is that rho I, so it could be like for ARP process I can have like 5 rows, okay, for ARP process. So rho I is not equal to 0. So any of the rows, if they're not 0, so if there is some sort of autocorrelation is present, so I will say that, well, the autocorrelation is present, so the null hypothesis of no autocorrelation is no longer true. Okay, so this is the null hypothesis, but we have seen previously that we cannot really do it for the population. So we actually take some samples, and what we do there, we actually take, let me use a different, or I can actually reduce the size here. So what I do there, let me use a different color. I actually estimate the ut and I run the regression. So let's say I have some gamma 1 ut minus 1 hat plus gamma 2 ut minus 2 hat and plus some gamma 0. Okay, plus some gamma 0. So that is basically, we have seen previously how we get this. Now here the null hypothesis is going to be this in the same manner. Null hypothesis is going to be my gamma 1 is equal to gamma 2 is equal to 0, and alternative hypothesis is going to be gamma I is not equal to 0. Essentially the gamma, from gamma you are sort of getting an estimate of rho, okay, because you cannot get this for the population, so you are actually estimating gamma, and from gamma you are actually getting an estimate of rho. Okay, so that is the idea. So that is the idea for a higher order error process of the error term, and how do you actually have your null and alternative hypothesis for autocorrelation. Okay, alright, so now I'll come down to the second point where I can introduce a lag dependent variable. Now let's go back to our main equation here. Okay, so let's say our ut is related to some of the xt's. Okay, now the error term is related to some of the independent variables. So what happens here, so there is some endogeneity problem. Okay, so error term is, and the x variables, so they're supposed to be independent. The ut is supposed to be independent of all the xt's, and that is where the Gauss-Markov assumption of zero conditional mean of error is so important. But if ut is not independent of x, so then u is going to be biased, and then the expectation term of this is not going to be equal to 0. So that is not basically, that is essentially violating the OLS regression condition. Okay, so we need to sort of ensure that. And how do I ensure that? So if I have, let's say if I have in my regression equation, if I write down, again I write down this equation, let's say this equation, I could have actually numbered this equation. So let me actually number this equation. So let's say this is my equation 1, this is the main equation I have written, and then I have written down this equation, equation 2, and then I have written down equation 3. Okay, and here I have, let's say I'll write down equation 3, but I will now think about this relationship. I'll now think about the fact that ut and xt are somehow related. So this condition is no longer correct, so I have to sort of, you know, do some error correction to take care of this bias problem. And so to do that, I'll just rewrite the equation first. So let's say I write down ut is equal to rho 1 ut minus 1 plus rho 2, gamma 2 ut minus 2 hat, plus I already have a gamma 0, so I'll write it at the end of it. And let's say these xt's are related, so let's say I have a gamma 3 xt1, the variable name was xt1, and then I have a gamma 4 xt2, and then I have a gamma 0 like I had as the intercept term. So now why I am actually including these independent variables in my regression equation is because since they are related with error terms, so it is important that I sort of introduce them in the regression equation so that I can make them free of these influences. Okay, so that is the idea why I introduce these xt terms to the in the regression equation when I'm regressing, when my ut is my dependent variable. So while I do that, essentially to make things simple, I can actually replace this xt1, xt2 with the lag dependent variable with the yt variable, okay, the dependent variable, because the xt's are actually determining yt. So if I include yt, so that would essentially take care of the bias problem that we have. So essentially we can write this equation as gamma 1 ut minus 1 hat plus gamma 2 ut minus 2 hat plus some, let's say, gamma prime, let's say yt minus 1. I have taken lag dependent variable of previous period, so we can take other periods as well. So this is my regression equation. So my regression equation, when I do this correction, so my regression equation is going to be this. So now this is the final equation I got for the Bruce-Godfrey test. Okay, now I'll be doing this regression. Now how do I know? Now I have to sort of decide some decision rules based on which I can say the autocorrelation is present or not. Okay, so the first test is that a very simple one. We essentially see the r square value of this regression in this regression equation. If the r square value is high, we say that the model is good. So the variables, the independent variables, are actually determining the dependent variable, and the independent variables are essentially the previous period error term or the lag dependent variables. So then that would mean the autocorrelation is present in the model. Okay. Now the second way to identify is that basically to check the F statistic. Okay, so we know that F statistic is actually helpful to determine the joint significance of a model. So what do we mean by joint significance? So essentially, if all the variables are actually making sense, if the model is making sense, okay, so how do we do that? So we have seen it in case of OLS process. So in OLS process, what you have seen is that if, let's say, F statistic that you calculate is higher than F critical, so then we say that the model is significant. So essentially, if we have, let's say, F critical is here, and then you have F calculated is here, so then you say that your model is actually having significance. So there is autocorrelation structure present in the model, right? So this is how we use F statistic. We are already familiar with this. And what is the null hypothesis here? The null hypothesis, rho 1 is equal to rho 2, and whatever other row you have is equal to 0. And alternative hypothesis is any of the row is not equal to 0, right? Now, so we do that. So there is another way of actually identifying, or actually, taking a decision based on the Bruce-Godfrey test, and that is basically we have n minus p, where n is the number of independent variables and p is the order of the AR process, into the r square that you obtain, that actually follows a chi-square distribution with p degrees of freedom. Okay, so this is called Lagrange multiply test. The sample size has to be large. Lagrange multiply test, or LM test, sometimes it is called LM test. So the idea is that if the chi-square value, so chi-square value essentially is this, and if the chi-square value that you calculate is greater than chi-square critical for p degrees of freedom, chi-square critical. So then I will say the model is significant. That is, there is autocorrelation in my model. Okay. So one point that we need to note is that the test 2 or the decision rule 2 and decision rule 3 are there, or the test 3, they're essentially the same or similar, because the chi-square distribution and F distribution are similar. So then the results that we get by using this 2 or 3 would essentially give us similar kind of result. Okay, so that is how we sort of use the Bridge-Godfrey test to identify the presence of autocorrelation in my model. So far we have discussed the theory part, and in the next lecture we're actually going to do some hands-on to show autocorrelation. We'll use data, we'll use R, using R, and we'll also show you Darby-Watson statistic, Bridge-Godfrey test, and so forth. So with this we'll end this lecture here. Thank you.